Experiment to oxidize phenylmethanol, benzyl alcohol, to benzoic acid with potassium manganate 7 solution, potassium permanganate, in alkaline conditions. In this experiment, you will prepare benzoic acid by oxidizing phenylmethanol, which is also called benzyl alcohol, using potassium permanganate in the presence of the base sodium carbonate. The balance equation for the reaction is shown on the screen. There are 7 main stages in carrying out this experiment. The first stage involves mixing the reagents. Using a dropper, 1 cm cubed of phenylmethanol is measured into a 10 cm cubed graduated cylinder. The 1 cm cubed of phenylmethanol is then added to a 250 cm cubed conical flask. Using a graduated cylinder, 25 cm cubed of saturated potassium permanganate solution is added to the conical flask. Then, 0.5 grams of sodium carbonate is added to the conical flask. The conical flask now contains the 3 reagents, phenylmethanol, potassium permanganate, and sodium carbonate as shown on the screen. The potassium permanganate solution is saturated to ensure that sufficient is present to oxidize all the phenylmethanol completely to benzoic acid. The sodium carbonate ensures that the solution is alkaline, as this oxidation works best at an alkaline pH. That is, the rate of reaction is greatest under alkaline conditions. You may notice a smell of almonds due to the fact that some benzaldehyde has been formed. The next stage involves heating the reagents to get the reaction to take place at a reasonably fast rate. The conical flask is clamped in a beaker of boiling water for about 20 minutes. As the reaction proceeds, the colour changes from purple, which is the colour of the manganese ion in an oxidation state of +7, to brown, the colour of the manganese ion in an oxidation state of +4. That is, there is a reduction of manganese in an oxidation state of 7 to manganese in an oxidation state of 4. The phenylmethanol is oxidized to benzoic acid. Note also that a brown precipitate is formed. This is manganese dioxide, which is not soluble in water and has the formula MnO2 as shown on the screen. On completion of 20 minutes of heating, the products formed in the flask are cooled by running some water from the top over the outside of the conical flask. The products in the flask consist of sodium benzoate, manganese dioxide, potassium hydroxide, and water, as illustrated on the screen. The compound sodium benzoate is produced as an intermediate in this reaction, and we will convert this to benzoic acid in the next stage. In the fume cupboard, 4 cm cubed of concentrated hydrochloric acid is added drop by drop to acidify the solution. Gloves are worn to ensure that the acidic solution does not come into contact with the skin. It is necessary to add concentrated hydrochloric acid in order to convert sodium benzoate to benzoic acid according to the reaction shown on the screen. Since benzoic acid is only slightly soluble in cold water, this helps to precipitate out the benzoic acid. In addition, the hydrochloric acid neutralizes any excess sodium carbonate and the potassium hydroxide produced in the reaction. The third reason for adding the hydrochloric acid is to provide an acidic medium to enable the Mn4+ ions in the manganese dioxide to be reduced to soluble Mn2+ ions as shown on the screen. When all the HCl has been added, a glass rod is dipped into the conical flask and the end of the glass rod is touched against a piece of damp blue litmus paper. This is done to check that the contents of the flask are acidic, that is, the blue litmus paper turns red. The stirring rod is left in the conical flask to avoid loss of yield of benzoic acid. In the next stage, sodium sulfite is added to the flask. Sodium sulfite is a reducing agent and reduces Mn4+ ions, which are insoluble, to Mn2+ ions, which are soluble. It is necessary to reduce the insoluble solid specks of brown manganese dioxide, MnO2, before filtering off the benzoic acid crystals, as these brown specks would contaminate the benzoic acid. The half reactions are shown on the screen. Using a dropper, sodium sulfite solution is added to the conical flask until the brown precipitate of manganese dioxide has fully reacted and the solution becomes clear. About 10 centimeters cubed of sodium sulfite solution is usually needed, but, if necessary, more than this quantity is added until the solution goes clear. When adding the sodium sulfite solution from a dropper, the dropper is used to wash down the inside of the conical flask to try get all the brown specks of unreacted manganese dioxide into the bottom of the conical flask. The flask is swirled well to make sure that there are no brown specks of unreacted manganese dioxide in the flask, as this will contaminate the crystals. Note that white crystals of benzoic acid become visible as the brown precipitate disappears. The conical flask is now placed in ice for about 10 to 15 minutes. Since benzoic acid has low solubility in cold water, placing the conical flask in ice helps to maximize the yield of crystals. The crystals are filtered off using suction filtration with the aid of a Buchner flask, Buchner funnel, and filter paper. This type of filtration speeds up the filtration process and also helps to dry the crystals. The conical flask is rinsed out with the filtrate from the Buchner flask to remove any crystals of benzoic acid that remain in the conical flask. The crystals are washed with ice-cold water to remove any soluble impurities that may be present on the filter paper or adhering to the crystals. Place the damp filter paper containing the crystals on a clock glass and allow the crystals to dry overnight. When the crystals have dried, use the laboratory balance to record the mass of benzoic acid crystals formed. Finally, calculate the percentage yield of benzoic acid as shown in the Chemistry Live textbook. This concludes the experiment.